Yes. Hello everyone and welcome to the live session. I hope you people are doing well. And yesterday only we have started a very important topic of organic chemistry, that is reaction mechanism. And there is something new about this lecture series, that this lecture will be completely in English medium, so that the students who face little problem in Hindi language, so the language should not be barrier between you and between you and me. That's why we have decided that this complete lecture series will be in English medium only. So, one very important information, because the lecture was not conducted on Monday, so this would be lecture number 2. So don't panic. Where is lecture number 1 and where is lecture number 2? This is the second lecture. Yesterday we have taken up the first lecture. Okay. So what we have what we were dealing with in yesterday's lecture was, we started with reaction mechanism topic. We saw how one should study this topic. We need to bifurcate this topic into few subtopics. For example, substitution reaction, elimination reaction, addition reaction, and further substitution reactions has many mechanisms which we need to study. For example, SN1, SN2. I have given you the brief idea how these things can be uh, studied, and we have started with the very basic portion of the substitution reaction, that we were dealing with what are nucleophiles and how we can compare the nucleophilicity and with all these things. Good morning Manoj, good morning, very good morning to everyone to who have joined the live, and do comment, and please uh, take care of one small thing. Let the session be an interactive session. You can also comment, you can ask your doubt. If you are watching this lecture series in recording also, then you can leave your comments after the class. I will surely reply you there. So moving ahead, what we have studied yesterday, we started with this reaction mechanism topic. We have divided this topic into few fragments. For example, substitution reaction, elimination and addition. If you are specifically working for gate or net, then a few more topics are added into this. Of course we will cover whole topic. uh, if we prepare for CSIR net exam, then automatically we are preparing for other chemistry exams, because CSIR net syllabus is very vast. It covers each and everything, so no need to worry about that. Good morning Brajraj ji, good morning chemistry wives, very good morning to everyone. So in substitution reaction, we were seeing that we have to study all these mechanisms. Along with this, we have an electrophilic aromatic substitution part, which we will be covering. Before going to the mechanisms directly, I have started with the very general components of a substitution reaction. We see that the basic components involve substrate. These are following substrates which we can see in a substitution reaction. Of course, the very important component is a nucleophile, which we were comparing, that how if we are given 4 nucleophiles, can we arrange them into the increasing or decreasing order of their nucleophilicity. We were dealing with such type of questions, correct? Then we have product, of course, and the last component is the living group, and the solvent also plays an important role in deciding whether the nucleophile will be a good nucleophile, a bad nucleophile, how it is going to affect the reaction. These all things we need to study. Good morning Pooja, good morning. It's a small request to you. If you like the session, if you think yes, I'm able to understand the whole concept, do like and share the video. Talking about nucleophilicity comparison, there are few factors which we need to check, and we need to proceed in the same chronology. First, we need to check size, then we need to go with electronegativity, stability of the anion, and the last factor which we will be comparing is called as hindrance. In the yesterday's lecture we saw that if size of an anion is very big, it means it can be very easily polarized. We can deform its size, and um, because of this, the anion is very much nucleophilic as compared to a smaller size anion, because in order to attack into the sigma star orbital, the smaller size anion goes very close to the sigma star, where it faces repulsion with the bulky CH3 group, whereas the bigger size anion takes advantage of its polarizability and can donate electron density without any hindrance. That's why bigger is the size of anion, more is the nucleophilicity. Usually books also write it as if you move down the group in the periodic table, the nucleophilicity increases. Now, this was about size. Sometimes the size factor does not work, and when we go with electronegativity. What does electronegativity suggest? If the nucleophilicity, if electronegativity of a center is very high, it means its nucleophilicity is going to be low. We say that in moving along the period, the deciding factor is always electronegativity. That's why in organic chemistry, we consider size along the period as same. That's why the size factors become same. Then we move to the electronegativity factor. There is a small concept of modified electronegativity, which if you are not aware of, then you can go through the GOC lectures where I have explained you how this works. A nitrogen which is sp3 hybridized will be less electronegative than a carbon which is a sp hybridized. This is a very surprising thing for us because a carbon is more electronegative than nitrogen, but this happens because of hybridization. Now, after this we saw stability. Of course, if I give you 10 crore rupees, then you will not be preparing anymore for your exams. You will be very much stable in your life. Similarly, the things works here also. If an ion is very stable, its nucleophilicity is going to be very low. On the basis of this, we have tried few examples. Now, the last factor which we need to see is hindrance. Now, what do you say about hindrance? If I increase hindrance, whether nucleophilicity is going to increase or it is going to decrease. What do you say about this? What's your view about hindrance? Good morning, spread peace. Good morning to everyone. Do reply in the comments. If I increases hindrance, then what will be its effect on the nucleophilicity? It decreases. Very good. For example, let's suppose I have OH minus, I have CH3O minus, I have a carbon center which have 2 CH3 O minus and a carbon center which has 3 CH3s and a O minus. I have these 4 nucleophiles. We observe that when we move left to right, when we are moving left to right, the bulkiness of the groups are increasing. Bulky, we can write that bulkiness increases. When the bulkiness of the groups increases, then sure shot their nucleophilicity is going to decrease. Their nucleophilicity decreases, but their basicity increases. Now, for the first time, I have introduced in front of you the term basicity. See, we need to be clear about both these terms. What is a nucleophile and what is a base? There is a very small difference. Let's suppose you have a carbon-carbon-carbon chain and you have a halogen group here. And we also have a hydrogen here. Correct. Let's suppose we have an anionic center which is A minus. If this anionic center attacks at the carbon center and this living group is eliminated, then this A center is behaving as a nucleophile. Very good. Now, let's suppose we have another B minus center which rather than attacking at the carbon center is abstracting this proton and then the living group is eliminated, then such type of species will be called as base. It means when we are making our nucleophile bulkier and more bulkier, it is very difficult for it to approach this carbon center, attack at the center and eliminate the group. Rather than it prefers to abstract this proton without facing any sort of repulsion. It means on moving left to right, the basicity of the center is increasing. And such type of reactions are called as elimination reaction. Of course, when an anionic center is behaving as a base, it is going to do elimination reaction, and such type of anions which are attacking at the carbon center are performing substitution reaction. So this is how substitution and eliminations are related to each other. There is a very thin line between the substitution and elimination. We will be seeing that a single nucleophile has an ability to perform both as substitution also and elimination also. So how we are going to decide, I will be helping you out. There are some factors which we look to decide whether this reaction will be going via elimination path or whether it will be going via substitution path. There is a very thin line between these two things, but we can make a clear point over this concept with the help of a few factors which I will be telling you further in the lectures. Okay. So for now, if we increase the hindrance, then of course the nucleophilicity is decreasing, but the basicity of the center is going to increase. Good morning, Manisha ji. Very good morning. Now, so we have covered with the four basic terms. Now the main factor which we need to look is effect of solvent. Now tell me what type of solvent we choose if we are dealing with a substitution reaction. We choose a polar solvent or we choose a non-polar solvent, or if you have something else in your mind you can also tell me that. If I want to choose a solvent for a substitution reaction, let's suppose if you are performing an experiment into a lab, which type of solvent you are going to choose? Hanji. Yes, do tell me which type of solvent you are going to prefer. See, whenever we perform a substitution reaction, we generally, very good. Whenever we perform a substitution reaction, we have a substrates like this, which have a leaving group that is delta minus and delta positive. If our substrate is polar in nature, then you must have heard in your childhood days that polar dissolves polar, or you have heard like dissolve like. If you have a polar substrate, then of course the type of solvent which you are going to choose is a polar solvent. Now, polar solvents can also be classified into two parts. One is your polar protic solvent, polar protic solvent, and the second one is called as polar aprotic solvent. Now, can you tell me the difference between the two? What is the difference between polar protic and polar aprotic? There is a healthy chance, Prithwil. Yes, there is a healthy chance, but it depends how other has performed. See, when we talk about polar protic solvent, it contains those solvent which can perform hydrogen bonding. So one very important factor is hydrogen bonding, which you can find in the case of polar protic solvents, but in polar aprotic solvent, this hydrogen bonding is going to be absent. There is no such hydrogen bonding here. The second factor which you can look is ability to donate H plus. Polar solvents generally donate H plus very easily, whereas polar aprotic solvent, this factor of donation of H plus is absent. They do not donate H plus very easily. For example, if you have, you must have encountered very many examples with polar protic solvent, like water can be example, ethanol can be an example, methanol can be an example, and etc. These all are polar protic solvents. When I talk about polar aprotic solvent, then you must have rinsed your what we call the test tube in the days when you were in the, I think, graduation, with a solvent which was called as acetone, if you remember that. CS3 C double bond O. This is an example of polar aprotic solvent. CS3 C double bond O CS3. Some more examples can be like DMSO. What is DMSO, sir? Dimethyl sulfoxide. This is also an example of polar aprotic solvent. If you can tell me more. Polar aprotic solvent can also be like DMF, dimethyl formamide, nitrogen. We have two methyls, C double bond OH, and etc. 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 There can be much more examples for both of them. Yes, very good, Pooja. Acetone, DMF, these all are the example of polar aprotic solvent. In fact, DMF molecule is very important one also. I'm sorry, it is not visible if. When we will be covering spectroscopy topic, then also we will be meeting this solvent, that is DMF, because it has some special characteristics. It shows some special characteristics into NMR spectroscopy. So now we have two type of solvent. One is polar protic solvent and second is our polar aprotic solvent. Now, how they are going to affect a nucleophile, this becomes very important. Whether they are going to increase the nucleophilicity or decrease the nucleophilicity, this we need to learn it. So, the next heading will be the effect of polar protic solvent. Now, what do you think? Whether it is going to increase the nucleophilicity or decrease it? First, tell me your view, then I will be explaining this topic into detail. What's your view over this? If I put a nucleophile, let's suppose I have chosen an anionic nucleophile and I have put it into a polar aprotic solvent, then what will happen to its nucleophilicity? Whether it is going to increase, decrease, someone is suggesting, sir, increase. Okay, let's suppose we have two anions. One is a very smaller size anion and one is a very large size anion like this. Okay, we have chosen a polar protic solvent, let's suppose water. Okay, so water has oxygen H and H, where oxygen is delta negative and hydrogen is delta positive. Now this anion and this water molecule are able to show an interaction which is called as ion dipole interaction. Ion because we have an anion here and a dipole which is created into a water molecule. So this type of interaction is called as ion dipole interaction. Now there will be very so many water molecules which will be surrounding this anion and will be performing ion dipole interaction which is called as solvation. This type of interactions where the solvent molecule is performing with the anion can be called as solvation. Since we are using water as a solvent, we can also call this as hydration. When we use some other solvent, the term will be changed, but for in general, we can say this is called as solvation. Hydrogen, oxygen, hydrogen, delta negative, delta positive. So this type of ion dipole interaction stabilizes the anion very much. And if your anion is gaining some stability because of this solvation factor, then of course its nucleophilicity is going to be decreased. So in a polar protic solvent, always remember the nucleophilicity of the anion decreases. So we will writing here nucleophilicity decreases. Why decreases? Because of the solvation factor, the anion is getting stabilized. So if it is getting stabilized, of course then its nucleophilicity is going to decrease. So in polar protic solvent, always remember nucleophilicity decreases. Now we need to compare between a smaller size anion and a large size anion, which is more nucleophilic, because solvation is taking place with both of them. Now let's suppose if I have 10 water molecules, 10 water molecules will perform the solvation with a smaller size anion. It is going to hold it tightly and will surround it completely. Whereas the same number of water molecules are going to perform this ion dipole, or we can say solvation, with this larger size anion also. But since the size of the anion is very large, the extent of solvation will be lesser as compared to those with the smaller size anion. So I can write here it as what? The extent of solvation is less. I hope so you are able to get what I am trying to convey with extent of solvation. Extent of solvation for a bigger size anion is less as compared to a smaller size anion. Correct? If so, it is very much true that yes, nucleophilicity is decreasing for the larger size anion also, but if we compare an overall comparison, still a larger size anion is going to be more nucleophilic as compared to a smaller size anion. Yes, nucleophilicity has decreased into a smaller size anion also and a larger size anion also. But the extent of decrease is higher in a smaller size anion because solvation here is very much high. I hope so you get the concept. Extent of solvation is less. So if someone asks you, if I have chosen a polar protic solvent and I have these four nucleophiles, can you arrange them into the nucleophilicity order? Can you arrange these four nucleophiles in nucleophilicity order? Yes. If I have I minus, Br minus, Cl minus and F minus, then what should be the order? Very good. Sir, still the order remains same, which we were studying in the yesterday's lecture, that larger is the size of an ion, more is the nucleophilicity, and it also works in a polar protic solvent. But inside, we also know that, yes, nucleophilicity must have decreased little bit for each one of them, and the extent of decrease will be more for a smaller size anion as compared to a larger size anion. But the main effect which a polar protic solvent plays on a nucleophile is it decreases its nucleophilicity. So this can be the order. Now, since polar protic solvent is decreasing the nucleophilicity, then what's your view on polar aprotic solvent? Whether here the nucleophilicity is going to decrease or increase? What do you think so? Hmm. Now the nucleophilicity should increase or decrease? Yes, Pooja, chemistry wife, Swati, Manisha, increase. Very good. See, if I tell you the result first, when we observe the nucleophilicity in a polar aprotic solvent, it usually increases. So how does a nucleophilicity increases? What does a aprotic solvent does with the anionic center? See, there are many examples for aprotic solvent. I am choosing a very simple example of DMSO. This is a DMSO molecule. We can write this DMSO molecule as O minus, a positive here, a CS3 here and a CS3 here. Now the positive charge on the sulfur molecule is embedded inside this bulky CH3 group, this bulky CH3 group and this O minus group. These all three bulky groups, that is 2 CH3 and oxygen with a negative charge, is surrounding this positive charge and this is embedded deep inside this environment of bulkiness of CH3 and electron density of O minus. So now what happens? I will be choosing two anions, one a smaller size anion and again one which is anion which is of large size. By seeing this anion, the sulfur positive is going to come closer to this anion in order to do some ion dipole interactions, or we can say positive negative interactions, so that it can gain stability. So this sulfur positive is approaching this anion, but along with this, the groups along with sulfur, that is both the CH3 groups, this O minus group is also dragged with the solvent molecule. Now another solvent molecule will be approaching O minus, a CH3 group here, second CH3 here. One more molecule was approaching anion, a CH3 here and a CH3 here. Now what happens? Yes, this positive charge was approaching in order to gain some stability with the anion, but since the DMSO molecule have larger size CH3s also, O minus with electron density, there is a strong hindrance, or we can say there is a strong repulsion in the solvation sphere. A repulsion in solvation sphere. What is this solvation sphere? The solvent environment which is surrounding the anion is called as the solvation sphere. Now, because of this anion, this solvation sphere is getting very much destabilized. This is not so this stability which is coming because of repulsion is not digestible for the anion, and if we put a new electrophilic center, let's suppose a substrate, then it attacks very fast over the carbon center, so that this environment get disrupted and no more repulsion is faced into the solvation sphere. I hope so I am able to convey what I am what's the concept. See, I will be repeating once again. If I have an anion, the positive charge of the DMSO molecule is attracted towards the anion. Now, along with the positive charge, the bulky CH3 groups and the O minus is also coming. So, in the solvation sphere, there is lot of hindrance because of this anion. So, this anion attacks on the carbon center very fast if we put some electrophilic center. That's why we say that in a polar aprotic solvent, because of the repulsion in the solvation sphere, nucleophilicity of the anion increases. Nucleophilicity increases. Did you get the concept how the nucleophilicity is increasing? Please do tell me in the comments. No problem, Cam Diary, it's fine. It would be more easier for me if I would be using Hindi as a language, but I'm trying my best to communicate you with in English and explain all the concepts. Anion size is small. Yes. Thank you. Thank you. Now let's suppose if we have a bigger size anion, then what is going to happen, sir? Of course, again the solvent molecule are going to approach to show some interaction with the anions. So we have DMSO molecule here, we have a DMSO molecule here, we have a DMSO molecule here. But since the anion of a larger size occupies a very large volume, the solvent molecules are not that compacted in nature as compared to the case which were in the smaller size anion. Here the solvent molecules were in very close proximity because of the smaller size of the anion, but for the larger case or the larger size of anion, the solvents are not in that close proximity as compared to the previous case. That's why I can say that the extent of repulsion which the solvation sphere is facing here is little bit less than the previous case. So I will be writing at extent of repulsion in solvation sphere. Solvation sphere is less. I hope so you are able to get the concept. Do compare both of them. So yes, nucleophilicity is increasing here also, but the extent of increase is very much higher in a smaller size anion. So for the first time, what is going to happen is a smaller size anion will be more nucleophilic as compared to a larger size anion. So if I give you, let's suppose F minus, Cl minus, Br minus and I minus. And if I ask you, can you arrange these anions into the increasing or decreasing order of the nucleophilicity, then what will be your answer? Yes, examiner will mention that he is asking the question in polar aprotic solvent, or he will simply give an example, for example, DMF or DMSO. This type of examples will be mentioned in the question. During repulsion between the DMSO molecule causes to ease escape of anion to attack on the substrate. Yes, very good spread piece. This is the same concept. Yes. So in a polar aprotic solvent, now what is going to happen is a smaller size anion will be more nucleophilic. So F minus for the first time is going to be more nucleophilic then comes the Cl minus, then comes the Br minus, and then comes the I minus. Always remember, if examiner has mentioned polar solvent, polar protic solvent or polar aprotic solvent, then it's good, you know what to do. If examiner had not mentioned any sort of solvent, then you need to consider it as polar protic, or consider the situation which we have dealt in the yesterday's lecture, that as the size increases, nucleophilicity increases. That's it. You will not consider the case of polar aprotic until and unless it is mentioned in the question that yes, the examiner is using polar aprotic solvent. I hope so you got the concept. Because sometimes it becomes confusing for you. So if nothing is mentioned, then what we are going to consider? Then go with the simple rule that if the size increases, the nucleophilicity increases. So we know that for a polar protic solvent, nucleophilicity decreases. The overall order is the same. Larger size anion is more nucleophilic. We also know that in a polar aprotic solvent, nucleophilicity increases. Now the things has turned, a smaller size anion is more nucleophilic. So we have deal with the which four components. I think we have dealt with what are substrates, we have dealt with nucleophiles, we have dealt with solvent, and of course product. Nothing to tell about product, but the fifth component which will be important is your living group. See, if I talk about living groups, whenever we see a substrate, let's suppose we have a R group and we have a living group attached here. Now, if any living group is eliminated, it generally takes a negative charge over itself, correct? And this carbon is going to get a positive charge. So, if the anion which is eliminated, for example here this Lg minus, if the anion over this center is very much stable, then we say that yes, the living group ability of the group is very much high. In order to make some notes in the copy, you can write this point also, that a living group is generally an electron withdrawing group. So it creates a partial positive charge on the carbon atom. This is what I explained to you. Generally, in most of the cases, the living group is going to be a withdrawing group, which takes the negative charge over itself and it's get eliminated. And if the stability of the anion is very much high, if stability is high, then we say that yes, it is a very excellent living group also. Its living group tendency is very much higher. Got it? Sir, if aprotic not mentioned, uh, your comment is not visible to me. Acha. Only protic will be considered always. Spread quiz, if aprotic is not mentioned, then you go with a general case, what we have studied in the yesterday's lecture, that when we go down the group, size increases, when we group down the group, size increases, nucleophilicity increases. When we move along the period, electronegativity increases, nucleophilicity decreases. Then apply that general rule. If the solvents are mentioned, then you will apply the concept of solvents. Got it? You can make notes of these few points also. This may help you in revising your lectures. But the basic concept says that if the anion which is eliminated, its stability is higher, then the living group ability for that case will be also very good. So I have written some orders for you. You may note down this order into your notes. This will be helping you out. This is a living group ability order. Living group power, you can say that. The group which you are looking at, this first center, is called as triflate group. This is called as triflate. This triflate is generally termed as a super living group. Super living group. What does super living group means? That it is a very excellent living group in all of this. Why? Because we have a CF3 group here which can stabilize this anion very much. That's the reason. And then comes a group with a phenyl and a Br group, because halogens do show minus I effect. They are deactivating in nature. That's why this is at the second place. Then comes the CS3, then comes the simple phenyl. Then this is your mesylate group, I minus, Br minus. This order may help you in some questions. It's good to note down and keep it in your notes. This order is telling about the living group power or living group ability of different groups. I minus, this order is also very important. This may be new to you. I minus, Br minus, then CF3COO minus. Water being neutral is also very good living group. Then comes Cl minus, F minus, then comes your acetate ion. Okay. The reference of this book is an Indian author book, which is Jagdamba. I think you must have heard about it. So this is how we decide whether a group is going to be a good living group or a bad living group. Always we compare and go on the basis of stability of the anion. Okay. Now I want to spend few minutes on the molecular orbital approach of a substitution reaction also. When we do a substitution reaction, then which orbitals are involved from the substrate side and which orbitals are involved from the nucleophile side. This also becomes very important. So you may write the heading as MOT approach for substitution. Molecular orbital theory approach for substitution. So there are two ways to study substitution reaction or reaction mechanism topic. One is a simple classical approach, which we were doing just now, and the second approach is a molecular orbital approach, which may also be used to explain the things, but we will not go with a very broad picture here, but a small we will take small idea how MOT works here. Let's suppose I have a very simple substrate of CH3X and a nucleophile. Since this nucleophile is attacking at this center and X is eliminated, we get the product as CH3 and a nucleophile, and the living group is eliminated. Now, if I ask you which type of orbitals are involved here and which type of orbitals are involved here, can you tell me what molecular orbitals are participating from both the side from the substrate side and from the nucleophile side? श्री क्लासरूम्स जेई वाला देख सकता है क्या? देख सकता है जी श्री क्लासेस. अभी तो हम बहुत बेसिक चीजें ही डिस्कस कर रहे हैं, बिल्कुल देख सकते हैं आप. बताएं भाई. From the substrate side, what orbitals are going to involve, and from the nucleophile side, which orbitals are going to be involved? Sigma, sigma or anti-sigma. Okay. Very good. See, if we look at the substrate pictures, if we look at the substrate side, what we have is we have a sigma bond here, and we must be having a sigma star orbital here. Sigma bond, sigma will be your bonding molecular orbital, and this is going to be your anti-bonding molecular orbital. How it has been formed? We must have a carbon which belongs to a second period, and we have a halogen which if it is a Cl, then it would be belonging to the third period, or we can just write it as X. Now what happens from the carbon side and from the halogen side, when the orbitals overlap, we have two molecular orbitals. One is the bonding molecular orbital and second one is the anti-bonding molecular orbital. Since this sigma bond has two electrons, these two electrons will be into the sigma orbital. Now, when this substrate accepts the electron density, then of course it is going to accept in the orbital which is vacant, and the sigma star orbital is the vacant orbital for the substrate. So the incoming electrons from the nucleophile enters into the sigma star orbital. If I ask you about the bond order before the electrons has been donated to the substrate, then it will be number of bonding electrons minus number of anti-bonding electrons divided by 2, which comes out to be 1. And of course, sigma bond has a bond order of 1. But once a nucleophile has donated its 2 electron into the sigma star orbital, then what will be the bond order? So if 2 electrons are present into the sigma star, then the bond order would be 2 minus 2 divided by 2, which is 0. This is suggesting us that yes, the sigma bond between carbon and halogen has been breaked. This is what you do when you follow the classical approach. We attack on the carbon center and the X group is eliminated. MOT is also saying same. When we see the bond order, it has become a 0. So from the substrate side, the orbital which is involved is your sigma star orbital, which you called it as LUMO also, lowest unoccupied molecular orbital, because this is your HOMO, highest occupied molecular orbital, and this is your LUMO, which is lowest unoccupied molecular orbital. Now, from the nucleophile side, you must have studied very few examples of MOTs in your inorganic, where you must have heard MOT of OH minus, water molecules. You must have dealt with the MOT of CO also. Always remember, when I go on the nucleophile side, let's suppose we have very simple nucleophile water. So water has an oxygen which has 2 lone pairs, correct? See, oxygen has in total 6 valence electrons. 2 are participating in formation of bond. These valence electrons which are not participating in the bond formation are called as non-bonding electrons. Now, when you observe the molecular orbital picture of water, these non-bonding electrons are present at the highest energy level, which is called as the HOMO, and they are present into the orbitals, which is the non-bonding molecular orbital. Means the nature of the HOMO is called as non-bonding. So, when water donates its electron density, it does from HOMO side, and which type of orbital is involved? So non-bonding orbital is involved. This is very much important. A question can come into 2 marks of CSIR NET exam, that which orbitals are involved from the nucleophile side and which orbitals are involved from the substrate side. So here we have a sigma star orbital and here we have a non-bonding orbital. Did you get this concept of the two things? What is HOMO in the case of nucleophile and what is LUMO in the case of substrate? Chemistry Vibes is asking, sir, if the bond order is 0, then how the molecule is existing? So where is the bond? The bond has been breaking. See, Chemistry Vibe, I am talking about the bond between carbon and halogen. This complete picture is for carbon and halogen. Yes, you are correct. When the bond order is 0, the bond is not existing anymore. At the product side, does the carbon and halogen have any sigma bond? No. So, yes, you are correct. The bond doesn't exist anymore. Got it? Chemistry vibes. This complete picture for bond order that is 0 is for carbon and halogen bond. I am not talking about the new bond which is formed between the carbon and nucleophile. Very good. So this was a small picture for MOT. It may be extended to a little more higher side also, but for today's lecture, I am keeping this much only. I hope for the next lecture, I will be starting with SN1 reactions. And if you say I can cover more concept over this MOT also. What do you think? Should I get some deeper concepts of MOT or should I start with SN1 reaction? What you people want? Yes, please do reply in the comments. What you want that I should start with the SN1 reactions or you want we should go more deep into this molecular orbital picture. Complete concept? Okay. So for the tomorrow's lecture, we will go some more in deep concepts of the molecular orbital theory. We will see how the nucleophilic substitution reaction rate is affected with the help of MOT concept. Okay. So for tomorrow, we will be meeting with this MOT concept again, and we will go in the deeper of these topics. Okay. For now, thank you so much. I am keeping this much only. Let's meet tomorrow again sharp at 9 a.m. I will be taking small slots of classes, but the classes will be very informative for you, and it will be clearing your doubts and it will be clearing your base. I hope you enjoyed the lecture. Thank you so much, everyone. Take care. Bye bye. Let's meet tomorrow again on 9 a.m. sharp. Thank you so much and happy learning.